Yes. As per your suggestion, T2G orbital is of lower energy and of course EG is of higher energy. I want to know from you, T2G orbital decreases by how much amount, how much quantity? This decrease is by
4 dq.
4 dq.
4 dq. Brilliant. And increase is by
6 dq.
increase of EG by 6 dq. Purpose question is why there is increase or decrease? It's a barycenter. Why there is increase or decrease? Where three orbitals are there, a set which encompasses three orbitals, that's a triplet, that's a T2G set, it decreases by 4 dq, and the set which encompasses two orbitals, its energy increases by 6 dq. 4 and 6. There is a relation. Why that decrease and increase is there? What is the intention for that decrease and increase? What is the purpose for the splitting? Why splitting does occur? That's the question.
To maintain barycenter.
Brilliant answer. Yes, I'm happy to know the answer. That is the purpose. It's equilibrium position, no? As we also want the stability, we want to be in equilibrium. If you want to be a successful, if you want to score good, then to maintain that equilibrium, you have to study. Here, 5D orbitals are there, fields are different, axial orbitals are there, they experience one kind of field, non-axial experience different kind of field, but anyhow central position, equilibrium position is not to disturb. Brilliant answer that I noted, I found from you. Excellent, excellent. To maintain barycenter the same, there's a decrease and there is an increase in the energies. Very good, very good. Yes. Now let me know for tetrahedral what happens? Which orbital is of lower energy?
E.
Right. Okay. I think last time I discussed that. Okay. Next, T is a higher energy. That decreases by how much quantity? This decrease is by how much amount? Is from, you can say it's a barycenter. Decrease of E by how much quantity?
minus 0.6.
Here 6 dq is a decrease. Whatever the increase previously was there, no? That is a decrease here. Wherever E set is there and we are talking about the d orbitals, then the E set will be with the number 6 and T set will be with the number 4. So increase of T is by 4 dq and decrease is by 6 dq. Likewise, we have already studied, but I am again asking to work for splitting in distorted octahedral complex, and square planar complex. That you have to work. We will discuss it in next time if it is needed. Otherwise, firstly, I will go to the next point for the revision. So that while covering this unit number 2, unit number 1, revision will occur. So today I revised just the splitting in the crystal field theory. It's just a basis. All points are not covered, but just as a trial, randomly questions were asked. Then splitting in the octahedral, splitting in the tetrahedral, and other splittings you are supposed to do. Very important points are there. The distorted splitting. Yes. Anywhere any doubt to anybody?
No, sir.
No, sir.
Good, good. We are discussing stabilities of the complexes. And for stabilities, thermodynamic and kinetic, these two ways are there. Out of that, thermodynamic stability, thermodynamic considerations we are discussing. And this thermodynamic stability can be measured by means of different terms. The first term that I discuss is as the formation constant. That's the stability constant. Second term, last time I discussed instability constant. That's a reciprocal of the formation constant. Third term I discussed is a stepwise formation constant. Will anybody help me? What are the notations for stepwise formation constants?
Kn.
Yeah, Kn is a general. Yes, K1, K2, K3, and so on up to Kn. Kn is a one of the notation which is used for nth step of the production or the synthesis or the formation of the product or the complex. If particularly I have to say K1 for first step, K2 for second step, and up to Kn. What are those stepwise formation constant? Later on, one more stability constant I informed to you. What was the name of that stability constant? Stepwise formation constant is one. Then next was
Overall formation constant.
right. Overall formation constant. Sister, brilliant answers you are giving. This video, recorded video, I had not edited, therefore I had not published. It is not with you, but still you remember what happened in the last lecture. Brilliant. Brilliant. Overall formation constant, and it is represented by terms beta 1, beta 2, and so on up to beta n. Later on, I discuss one relationship between overall formation constant and stepwise formation constant. Now I want help from you. Beta n is the overall formation constant. That beta n is equal to,
K1 into K2 into
yes,
K3 dot dot
yes,
dot Kn.
yes, right. K1 into K2 into K3 and so on up to Kn. That is a relationship between the overall formation constant and the stepwise formation constant. Up to there we had discussed last time. Today we want to discuss a stability constant and factors affecting on the stability constant. Stability constant, different terms already we discussed. Now factors affecting or influencing these stability constants. Maybe it's a general formation constant, maybe it is a particular stepwise formation constant, say the nth step, maybe it is a overall formation constant, maybe it's a beta n. So those formation constant and the factors affecting on them, that we have to what discuss. Three main factors are there. Listen carefully now. Three factors are there about which we are what the discussing. The first factor is nature of metal ion. Of course, central metal ion. Second factor included in your syllabus is nature of ligands or coordinating groups. And third factor is presence of rings, as like there remains a rings, finger rings or ear rings, different ornaments, rings, circular, or you can say the disc shape. So those rings do remain in coordination compounds also, special category of coordination compounds. So that also affects the stability. So three factors are there which affect the stability. One, metal ion. Second, ligand. And third, presence or existence of the ring in the complex or ring structure of the complex. One by one, we are discussing them all. Is these three factors clear to you?
Yes, sir.
Yes, sir.
Yes, sir.
It
Yes,
is
sir.
just it is just the memory base. Only you have to time being remember this data. Afterwards, data means information plus application of the concept that we need to do. So let me consider the first factor. What was the first factor? Yes.
Nature of central metal ion.
Yes, nature of central metal ion, or only you can say metal ion. In that, the first point is charge and size. Out of that, let me discuss the first aspect, that is charge. And for that, in your book, they have given few examples. Sorry, spelling just you have to see charge. And examples considered are with different metal ions. Will anyone answer which metal ion show plus one charge majoritically
Hydrogen.
in periodic table? Yes,
Potassium.
right. Potassium, sodium, lithium, rubidium, cesium, francium. Who are they? What is their group number? In periodic table, where are those? Lithium, sodium, potassium, rubidium, cesium, and francium. Above them there is hydrogen. Simple question.
Group number 1.
Right. Group number one, out of that, let me consider a second element in the group number one. That's what? Lithium, which carries the plus one charge. Then let me consider one element from second group whose atomic number is 12. Help me. Which is that element with atomic number 12?
Magnesium.
Magnesium.
Right, magnesium. Charge is 2 plus. Let me consider element with charge 3 plus, which is below scandium, which is in third group. Below scandium. What is that?
It,
Right. Yttrium, which carries 3 plus charge. And last, I want to consider thorium, actinoid, which carries plus 4 charge. These all metal ions govern or bear different charges. As per my point of consideration, if charge varies, stability should vary. Stability should differ. What happens for these complexes? Especially if they combine with OH minus ion, hydroxide ion as one of the ligand we are considering. So how the stability varies, that I want to consider here. So here I am considering stability constant for a complex between Li plus and OH minus. Formula will be LiOH. stability constant, that's a K, between magnesium 2 plus and OH minus. If I represent MgOH, what will be the charge on MgOH? Help me. You know the charge on Mg2 plus, that only answer I given. You know the charge on OH minus. Yes, charge on MgOH will be
+2.
no Mg.
Plus.
Plus 1.
Right. Mg has 2 plus charge. Here 2 plus charge is there on Mg. Here 2 plus. And here OH has 1 minus, no? So combination, summation, algebraic summation of that, what will be there? That's a plus, not minus, plus 1. MgOH plus. If I consider hydroxide complex and formation constant, that's a K with yttrium, then YOH charge will be, charge on YOH will be, right, +2. Brilliant. Go on answering. Don't be shy to answer. If you answer, certainly that will help you. That's a stepwise formation constant for thorium complex. THOH charge will be
Plus 3.
right, +3. Now pay attention. Lithium +1 charge, Mg +2 charge, yttrium +3 charge, thorium +4 charge. Charge on the metal ion is increasing. Stability constants for them are, try to remember these numbers now. Stability constant for first complex is 2, merely 2, only 2. Stability constant for second complex with charge 2 plus, that's MgOH plus, is 10 raised to 2. It is not only 2, 10 raised to 2 means 100. See, 2 and jump is toward the 100. Stability constant for yttrium complex is 10 raised to 7. So 10 raised to 2 means 100. 10 raised to 5 means lakh. 10 raised to 7 means crore. We are going to 10 raised to 7. And stability constant for the complex with central metal ion bearing a +4 charge, that's a thorium, is 10 raised to 10. Repeat now. First number was 2. Second number 10 raised to 2. Third number 10 raised to 7. Fourth number 10 raised to 10. So what are you finding? Stabilities are increasing. So what is the conclusion? Conclusion is with increase in charge, I represent by Q, with increase in charge, stability increases. It is a conclusion from this discussion. I am discussing nature of central metal ion. Out of the 2 points in the central metal ion, charge and size, that's the first point, that's the charge and size. I discuss here only charge. For that I consider +1, 2, +4 different metal ions. Further I consider Li plus, Mg +2, Y +3 and Th +4 respective hydroxide complexes and stability constant values. Yes, students, are you understanding what I am saying?
Yes, sir. Yes, sir.
Let us repeat.
Yes, sir.
What was the stability constant for the first, that's the complex LiOH?
2.
Right. What was the stability constant for the second complex, that's the MgOH plus?
10 raised to 2.
Brilliant. What was the stability constant for the third complex, that's a YOH +2?
10 raised to 7. 10 raised to 7.
Brilliant. What was the stability constant for the fourth complex, that's a THOH +3?
10 raised to 10.
Right. These stability constants are increasing. Within stability constant increasing because charges are increasing. So with increasing charge, stability constant increases. That's the conclusion. Now my second point of discussion is size. So I need to consider such metal ions where sizes are varying, but charge should not vary because that factor I have to keep constant. No. So for that, let me consider a metal ions from second group, and I want to consider beryllium. Sorry. Let me consider higher. That's a large size. That's a barium. First, I'm coming to beryllium also. Barium +2, then calcium +2, then magnesium +2, and beryllium +2. All are second group. Beryllium I said at the beginning because it is a low atomic number. But I am starting my discussion of this point from high atomic numbered element, that's a barium. As we go down in a group, size increase. So barium is with the large size, calcium somewhat small size, magnesium little smaller, and beryllium further smaller size. So what is happening here? Size is decreasing as I shift or move from barium to beryllium. Students, are you understanding what I'm saying?
Yes, sir.
Yes,
Okay.
sir.
Then let me consider again the hydroxide complexes. So hydroxide complex for Barium, how can I represent? That's a BaOH. Help me. What should be the charge?
Plus.
Right, plus. Other CaOH. What should be the charge?
Plus.
Right. Third MgOH. What should be the charge?
Plus.
Good. Likewise, last BeOH charge is plus. These are the four different monopositive hydroxo complex of second group elements. Now, stability constants for them. Stability constants I am representing here by a simple term, that is K. And those stability constants were found to be for first complex BaOH plus, it is 4. For second complex CaOH plus, it is found 30. For third complex MgOH plus, yes, last time also you studied that, no? MgOH plus complex. What was the stability constant?
2.
2 was for what? See, first complex.
10 raised to
Of, right, 10 is to 2 is the correct answer. 2 was for LiOH. Students, are you understanding what I'm saying?
Yes, sir.
Yes, sir.
As MgOH, it is a 10 is to 2. 10 is to 2 means it is 100. But actually, it is 120. 120 is near to 100. Why for? Because variation was very large, no? To 10 is to 10 is to 7. Compared to that crore, that 100 is what? And 120. Both are same, no? Nearly same. Therefore, for the sake of brevity, for the sake of comparison, for the sake of simplicity, last time I represented the same stability constant as 10 raised to 2, means 100. But actually, it is 120. So if you represent there also as a 120, nothing wrong there. You are right there. But it will easy for remembering. Therefore, that representation was there. And for last complex, that's a BeOH plus, stability constant was found to be 10 raised to 7. See, these values are somewhat comparable, no? And therefore 120. If you write 100 also, nothing more serious. Here, understanding the relation is important. Understanding the variation is important. Okay, so for barium complex, the stability constant is 4. For calcium, it is 30. For magnesium, it is 120. And for beryllium, it is 10 raised to 7. Beryllium. See, barium is a large in size. Beryllium is a small in size. So what is the conclusion from this? Size is decreasing. If size decreases, then what will happen? Then stability will increase or decrease?
Increase.
increases.
Right, stability will increase. That's a relation. So it is the second part from the first point of charge and size that I discussed. At first I discussed charge, and now I inform you about the size. Let us revise that. 3 complexes I told to you. What was the first complex? Just I discussed that. What was the first complex? Which metal was there?
BaOH plus.
Right, barium. Barium is BaOH plus. Second complex was
Calcium OH plus.
CaOH plus. Third one, fourth one.
MgOH plus.
Right. Fourth one, last one,
Beryllium OH plus.
beryllium OH plus. Stability constant
4.
for calcium
30.
30.
30.
here.
120.
120.
See, how to remember 4 into 30, how much? 120. Means just playing with these numbers, it will be easy to remember. Instead of 120, if you write 100, then so nothing wrong there. Okay. And for BOH plus, considerable high number is there. What is that? 10 raised to 7. Okay. So 2 statements we are with. The first statement about the charge. When charge increases, stability increases. And or the second statement, when size decreases, stability increases. But if I have to represent it in one term, both I want to represent charge and size in one term. Charge is the one term and size is the one term at this moment for us. But if I have to represent it in terms of the only one aspect, then that aspect is charge density. Sorry. What is that charge density? It is a ratio between charge and size. It's a ratio, density, charge density. What do you think? This ratio, value of this ratio will be high, will be more, will be large if when it will be high, if charge is more, and it will be high if size is less. Could you able to understand what I am saying? The correlation? If no, then say no.
Yes, sir.
Yes, sir.
Yes, good. So if charge is more, density will be more. If size is less, density will be less. Which density? Charge density will be less. Our conclusion already is there. Charge is more, stability is more. Size is less, stability is more. It means if charge density is higher or more, stability for that complex will be higher or lower.
Higher.
Yes, stability will be higher. It is our the final conclusion for the first point. The point with which I started was the charge and size of the central metal ion. I specifically discussed the charge point. I separately discussed the size point, and at last I combined both and I brought one term. What is that term? What is that term?
Charge density.
Charge density. And that charge density, if is larger, if it is more, it is higher. Stability also will be the higher. It is a conclusion from till now discussion about this newly opened point. Yes, is it clear to everyone?
Yes, sir.
Yes, sir.
Yes, good. Now, second point. Second point under the central metal ion. It is a part of the central metal ion. And the second point for the central metal ion is, I think I said is A. So I say here as what the B. And the second point is crystal field effect. That crystal field effect also decides the stability. In that first unit, for the application of crystal field theory, variation of the stability of for the complexes, maybe echo complexes that you might have plotted. The graph was plotted. Explanation for those stability is in the concept of crystal field effect, or it is called as CFSE, crystal field stabilization energy. Higher the crystal field stabilization energy, more will be the stability that we have discussed last time. Last time is while discussing unit number 1. But the crystal field stability depends on what? Crystal field splitting. And what is that crystal field splitting? It is a part of the crystal field theory. So effect of crystal field, that's a crystal field effect, is a point of the discussion. It is found that second half of that first transition series element, if I start from the manganese, say Mn plus 2, the next element is Fe plus 2, next element is, yes, help me, what is that?
Cobalt.
CO plus 2.
Cobalt plus 2, next one,
Nickel plus 2.
right, next one,
C
copper plus 2, cuprum plus 2, you can say, next one,
Zinc plus
Zinc
2.
plus.
zinc plus 2. It is found that Mn plus 2 is less stable compared to Fe plus 2. I'm not talking about the metal ion. I'm talking about the complex of that metal ion. Complex of Mn plus 2 is less stable than complex of Fe plus 2. Fe plus 2 is less stable than CO plus 2. Yes, are you understanding what I'm saying?
Yes, sir.
Yeah. CO plus 2, sorry, is less stable than Ni plus 2. Cu plus 2 is more stable than Ni plus 2. Student, just a minute. Yeah. Cu plus 2 is more stable than Ni plus 2. It is a practical observation I am saying. And it is found Zn plus 2 is less stable than Cu plus 2. Just timing listen what I am saying. Afterwards, we'll conclude why that statement is there, why that logic is there, why that variation is there. The answer is in electronic configuration. Yes. Mn plus 2, how many electrons do remain? Anybody will answer. Mn plus 2 is how many electrons in Mn plus 2 outermost orbitals? What is the atomic number of manganese?
25.
25. So 5 is the last digit. So that those electrons will be there in dipositive oxygen state. So it's a D5 electronic configuration for Mn plus 2. For Fe plus 2, it is a D6. For CO plus 2, it is 7. For Ni plus 2, it is 8. For copper plus 2, it's a game of 9 electrons. And for zinc, completely filled orbitals. That's a D10. Because of difference in the number of electrons and arrangement of those electrons in the various d orbitals, the stability varies. If 5 electrons you have to arrange, you have to represent, then how will you represent those 5 electrons? In T2 orbital, how many electrons will be there? And in EG orbital, how many electrons will be there? I'm talking about high spin complexes. I'm talking about weak field ligands. I'm talking about less stable complexes. Say simple echo complexes. If 5 electrons are there, then how will you arrange those electrons? While discussing CFSC, I told you that point. Let me see whether you know it or not. See T2G and EG. Here if I represent 3 orbitals, say T2G and here EG, then first electron will be in T2G, second in T2G, third in T2G, fourth in EG, fifth in EG, because gap is less. 10 degrees less than the pairing energy. So what electronic configuration for D5?
T2G3 EG2.
2, right. For D6?
T2G4 EG2.
T2G4 EG2. For D7? Yes, helping.
T2G5 EG2.
Right. For D8?
T2G6 EG2.
For D9?
T2G6 EG3.
Right. I was waiting who says T2G7. T2G can't accommodate 7 electrons. T2G6 EG3 and last T2G6 EG4. These are the electronic configurations. So if you read these electronic configurations more particularly, then you will find compared to these 3 electron, here one more electron is added. One more electron is added. One more electron is added. Electron is not added in T2G. Electron is not added in T2G. On the other hand, it is added in EG and is added in EG. Crystal field theory for octahedral complex we have studied. T2G orbit is of lower energy, and if electron goes in the lower energy means lower in energy total. Stability will be more stable complex will be there if electron goes in T2G, and less stable will be there if electron goes in higher orbital. So EG, because T2 is a lower energy, it will stabilize the complex. Are you understanding what I'm saying? Yes or no? If no, then also let me know.
Yes, sir.
Yes, sir.
Okay, so here see,
Yes, sir.
there is an increase in the T2G orbital electrons compared to this T2G3, T2G4. So suppose a stability is likewise, one correct mark. Here stability will be more. Here stability will be furthermore. Here stability will be furthermore. So increase in the stability as I move from left to right, increase in the stability as I move from left to right, increase in the stability as I move from left to right. Up to here I could able to understand. It is digestible, it is understandable, it is simple, because electrons are entering in the low lying T2G orbitals, and because of that stability will be there. But I can't understand that this relation copper plus 2, how can it dare to be more stable compared to Na plus 2, because as per our concept, electrons are entering in EG orbital, and if electron enters in EG orbital, then this should be less stable. But what I am finding here, it is what more stable. It's a big question mark. Yes, are you understanding the question mark?
Yes, sir.
Yes, and what we are finding, Cu plus 2 is more stable compared to Zn plus 2. Here one can say, here 3 electrons are there in EG, and here 4 electrons are there in EG. In EG orbit electrons increase, so stability will decrease. So there is no question about this variation, copper plus 2 and Zn plus 2. Only problem is at what the copper plus 2 and Na plus 2. Why it is the variation? Other than that, crystal field theory is quite enough to explain this variation in the stabilities. Therefore, I can say crystal field effect affects the stability. But still, whatever I said, no big question mark, that also is answered by crystal field theory. But general application, when we say for the octahedral complex, then by simple logic, if electron goes into T2G orbital, more stability, next electron, ideal electron goes to EG orbital, stability will decrease. So other than the higher stability of copper plus 2, everything in these examples, in these metal ions, right from Mn plus 2 to Zn plus 2 are explained. That is the legacy of, that is the importance of crystal field theory. That is the crystal field effect. So I can say now crystal field effect affects the stability. Main problem is big question mark, and that big question mark was between Ni plus 2 and Cu plus 2. Actually, I was expecting Na plus 2 to be more stable, but what is found? Cu plus 2 is more stable. Why? Because of electronic configuration. Na plus 2 is a D8 system and Cu plus 2 is a D9 system. Will anybody answer what is the specialty of D9 electronic configuration? Specialty of D9 electronic configuration. Okay, to help you, I write the electronic configuration. D8 electronic configuration, the T2G orbitals I am representing, these are EG orbitals. Here T2G orbitals and EG orbitals. Let me represent the electrons within them. D8, first electron, second electron, third electron, fourth electron, fifth electron, sixth electron, seventh electron, and eighth electron. This is the D8 electronic configuration. For D9, how can I write? First, second, third, fourth, fifth, sixth, seventh, eighth, and ninth electron. What is the difference in these two electronic configuration? Don't say that EG has 3 electron and EG has 2 electron. No, here some one particular word is there, and because of that you have studied one theorem, or you have studied one kind of splitting. Means octahedral you have studied, tetrahedral you have studied. After that, before studying square planar, you have studied one kind of complexes. What are those complexes? Or you can say, because of this difference in electronic configuration, those complexes do occur. What is that electronic configuration? What can I say for the electronic configuration? How can I understand electronic configuration? So because of that, you have studied one theorem or one distortion. I help you. You have studied one distortion because of one theorem or name of the scientist. What is that? Yes, will anyone answer? I help you. The name of that scientist starts with J and surname starts with letter T. Say, here is a problem. You have to study. Distortion. Which distortion? Distorted octahedral complexes. Z in, Z out, that you have studied. Which theorem? That is called as that distortion. JT distortion means what? At least one student. Distortion for octahedral complexes can be explained by one theorem. Distortion theorem it is called. What is that theorem? JT theorem. JT. J stands for what? T stands for what? Okay, at least see that J for John. Then T for
Thomson.
no.
Taylor.
Taylor. John Taylor effect. John Taylor phenomenon that you have studied. Distorted octahedral complex. Have you heard this name, John Taylor?
Yes, sir.
Yes, that only I was asking. So John Taylor distortion, and that occurs due to what? What is this? Which electronic configuration? Which electronic configuration it is? It is, yes, complete.
Complex.
No, what type of electronic configuration it is? At least complete now. I wrote only first 5 letters. Remaining are to complete. What type of electronic configuration it is? At least complete. Complete spelling I wrote there. Read only that spelling, that configuration, that electronic configuration. Yes,
Asymmetric.
asymmetric electronic configuration. See here, here in T2G, 2 electrons, 2 electrons, 2 electrons. Symmetric. EG, 1 electron, 1 electron. Symmetric. 2 electron, 2 electron, 2 electron. Symmetric. But in case of EG, here 2 electrons are there and only 1 electron. It is asymmetric. Because of asymmetric electronic configuration, in order to govern the symmetry, complex will undergo distortion. And because of the distortion, splitting parameter increases. And because of increasing splitting parameter, stability increases. And that's the reason why copper plus 2 is more stable than Na+2. Answer is not only in simple calculation of T.Y.B.Sc for octahedral complexes. We have to consider what type of actual complexes are there for copper plus 2. Distorted octahedral complexes are there. Z out complexes are there. And because of that, copper plus 2 is more stable. So what I discuss now, crystal field effect is the point of discussion. And I represented the metal ions from the transition series, and those metal ions from the transition series which were there, one is Mn plus 2, second is Fe plus 2, cobalt plus 2, Na plus 2, copper plus 2, and Zn plus 2. As per the electronic configuration, it was expected that Fe plus 2 more stable, Cu plus 2 more stable, Na plus 2 more stable, and Cu plus 2 should be less stable. Such should be there. But what is the reality? Reality is Cu plus 2 found to be the most stable, and that more stability of Cu plus 2 is due to asymmetric electronic configuration, or is due to distortion. Who had answered that distortion? Of course, crystal field theory. So I can say crystal field effect can answer the stability of the complexes. So under nature of metal ion, it is a second point, and that second point is crystal field effect. Is it clear?
Yes, sir.
Yes, sir.
Yeah. So, students, today I discuss factors of thermal stability. First factor, charge and size. Charge separately, size separate, and combined point. Second factor, crystal field effect. One variation I told to you. And explanation of variation lies in the crystal field theory. Therefore, we said crystal field effect matters for the stability of the complexes. Next time, we'll continue our discussion. Is today's discussion clear?
Yes, sir.
Yes, sir.
Yes, sir.
Yes. So if you have doubt, next time we'll have the further discussion. I stop the discussion and I'm attempting now to complete the all videos to upload them. Okay, give me some time. I'll work for that. Within 2 days, I want to finish all the things uploading. Probably today only. Okay. Thank you for attending lecture. Let us wind now. Quit now. Lecture is over.